one of the big challenges in looking at gamma ray bursts is that requires input and expertise in many different fields of physics, and not just physics, also computer science. In physics, you have to understand general relativity because some of the energy, much of the energy, comes from matter falling into a black hole. There are black holes involved, so you need general relativity. You also need to understand how the matter flows, that is relativistic hydrodynamics. Magnetic fields are probably very important, and so is radiation transport of the gamma ray bursts and of neutrinos that take part in these systems. And these are really separate subfields in astrophysics, and some of them are computationally more advanced, some are computationally less advanced, and bringing everything together and understanding it in one coupled model, that is our goal that we want to address in the coming years.
The gamma ray burst problem is the latest problem that we're looking at in a long line of research that's gone on in this group for the last 20 or so years actually, and the whole field goes back to something like the 70s when people started using computers to look at simple black hole problems, and we've been building the infrastructure, not myself but others, since that time, and our group very actively in the last 10 or 20 years to look at black hole simulations, to look at neutron star simulations, and now we have all the infrastructure in place, and we're getting the science in place to look at this the grand challenge problem for the gamma ray bursts. So we have a number of awards that by chance actually have come at the same time. It's really part of a strategic plan that we have for how to address this, because it isn't possible. This is such a large problem. It really can't be easily undertaken by a single faculty member or a single postdoc, and we have to think about the physics, about the computer science, about the visualization, about the whole infrastructure that's needed to support this in terms of having resources to run simulations on, storage to hold the data. So it's a very big agenda that we have. We've been fortunate enough to be successful in 4 or so grant proposals that we made to NSF earlier this year. And they really come together to provide a very synergistic support for this project. So one is called CIGAR, and this funding is towards providing a community infrastructure for problems that use general relativistic magnetohydrodynamics, which actually covers a very broad spectrum of problems that involve hydro. And this is in this funding we want to really engage the community in coming together around a single code base, so that we develop software that can be used across the whole community worldwide and raises the level of what people are able to do. If we're all using the same software, that software will be better written. We want to have the community contribute to it and advance it. And it will stop having individual groups have to write their codes from scratch and try and get people to work together. And then we have the PetaCactus award that Erik is leading, that's really doing the fundamental physics problem, actually trying to solve the gamma ray bursts, building on this infrastructure that we will develop. Another award is a PRAC award, which stands for Petascale Resource Allocation Committee, I think. And this is going to provide access to the Blue Waters petascale facility that's being built at the University of Illinois. This is going to be a petascale computer that will be online in maybe as early as 2011 or thereabouts. And we are one of the a couple of dozen applications that is going to be working with the team up there to prepare our application to be ready to work in this environment. And then the last award is looking at distributed visualization, and there we're really interested in how are we going to we want to solve this problem. It's going to use petascale computers. It's going to create a lot of data, petabytes of data that we need to visualize. And it's an immense challenge on how to manage that data and how to visualize it. In the end, if we just have data, then we don't have any insight into physics. To get the insight, we need to do visualizations. We need to analyze the data and be able to experiment with the data that's come out of the simulation. And in this award, we'll be using high-speed networks such as those that are here in the Lonnie environment in Louisiana, state-of-the-art networks, and understanding how now these networks can really enable science in that they give us unprecedented bandwidth, very low latency to data, and we want to be able to use these networks in new ways to help with the visualization of the data.
So the infrastructure that we are developing that solves these equations can be used for other physical applications as well, not just gamma ray burst. A current topic where there is a large collaboration in the US and also in Europe, actually on the whole planet, is regarding binary black holes, systems of two black holes that merge, emit gravitational waves, and the gravitational wave will be detected by LIGO in a few years once LIGO has reached sufficient sensitivity. Other systems that people examining are systems consisting of black holes and neutron stars, binary neutron stars, or single rotating neutron stars that would also emit gravitational waves. And these are systems that are examined by different research groups, and they could all, in principle, use the same infrastructure that we are developing. Once we make improvements, these improvements would also benefit them because they can get to a solution that is more accurate or can achieve a solution in a shorter time or use fewer computational resources for that. And other advantages are also that if there's a common test, common validation problems, then it is clear that the code is actually well tested, that the algorithms are correct, that the physical models built into these systems have been validated and are believable. That reduces the load on the individual researcher when they prepare a publication. So the Alpaca project is an ongoing project that started about 2 years ago. It turns out that when you want to solve these problems in relativity, you need supercomputers to do that. You need large resources, and these are very complex programs that consist of different components addressing different parts of the physics or of the computer science. And putting these programs together and then ensuring that all the components interact nicely, that the result is actually correct, and that things work efficiently is a very complex task. And the tools that exist currently to debug problems on supercomputers are not sufficient. We need better tools for that, and this is the goal, the main goal of the Alpaca project, to develop tools and to make the community use these tools, to help the community use these tools that make it easier to write correct programs that runs on thousands or in the future of hundreds of thousands of cores, and also run efficiently there without wasting most of the time.
The Scale 09 competition that's organised by the IEEE and was held this year in CC Grid in Shanghai. This is a competition that's looking for scalable real-world applications. So, and we entered that. And this is actually the entry that we had was a kind of prototype of the work that's going to be going on in this broader PetaCactus project in the future. We showed how we can already scale up our cactus and carpet infrastructure to model black holes. We ran a production simulation on 2,000 cores of a supercomputer in Texas as part of the National TerraGrid. And then we also showed how we can use distributed visualization to look at the data that came out of that simulation. So one of the challenges here is as we generate more data for the visualization, you want it to be interactive and immediate. And we showed how you can build a new system for visualization that's fundamentally built with high-speed networks into the design of the architecture of the software that could be very responsive, could read data very quickly, and provide interactive visualization. And now the challenge is to take these components, and this is what we're going to be building on in these projects that we've talked about, to extend the physics to gamma ray bursts and to extend the scaling of our simulations. We basically want to scale from 2,000 cores, running on 2,000 cores simultaneously as we are now, up to hundreds of thousands of cores. It's a very big challenge. Luckily we have a number of projects and funding and motivation to do this.
I would like to emphasize that the important thing of what we demonstrated in Scale 09 was that we did not just run simulations on a supercomputer. That is only a small fraction of the actual problem. In real life, in research, you start with a particular physical model and then you have to implement that model in a code. So we used automated code generation to generate efficient kernels starting from, in this case, from the Einstein equations. We ran the simulation there and then we used the post-processing and the visualization that Gabrielle just described. So running something on a supercomputer is just a small fraction of the problem, and it has to be embedded in an overall approach.
So I think one of the important things about our team here is that we are composed of students and faculty from the departments both of computer science and physics. And for us, it's very important from my point of view, from working from computer science. I want to work with real-world applications to solve problems, real problems that people actually have, problems that are important in the world today. And we have this synergy between having the science motivate the computer science research, and then the computer science research, we turn that into production tools that can actually enable the science. And this is a kind of delicate balance sometimes, but I think it's very important. I think it serves as a very good model for how to advance science in both areas. It's very good for the students. It's very important now to train students in interdisciplinary research and also in real world problems, so that they're not just devising new algorithms that are maybe not relevant to any real application. And so we have students in the group, both from computer science, from physics, from other disciplines, undergraduates, graduate students, and postdocs. And I think this leads to a very lively atmosphere for the kinds of research we want to do.
What I see in physics, in the physics curriculum, is a bit of a gap between what is taught to physics students, how to program, and what one actually needs in research. So supercomputing, HPC programming is quite complex, and I don't see this being part of the undergraduate physics curriculum today. I think there's something we need to do to bridge the gap and to solve the problem, to make computational methods a more important part of the physics teaching, if students are interested in that and see their career going in this direction.